Hi. In the previous lecture series, we were talking about the computer components like central processing unit, memory, and input-output devices, and the generations of computer. We started with the first generation to fifth generation. We covered their characteristics. In today's series, we are going to talk about computer architectures and the great ideas in computer architecture. So, here, what is a computer architecture? So, computer architecture is a set of rules and methods that describe the functionality, organization, and implementation of computer systems. So functionality means how it is going to perform the different operations. It may be the arithmetic operations or the logical operations. And then we are going to talk about how these operations are organized and how they are implemented on processor and programmability side. The architecture of a system refers to its structure in terms of separately specified components of that system and their interrelationships. So, what are those? The architecture's structure. You can see first of all a typical application, such as a word processor or a large database system, may consist of millions of lines of code and rely on sophisticated software libraries that implement complex functions in support of the applications. As we will see, the hardware in a the implementation the hardware in a computer can only execute extremely simply the low level instructions. So to go from a complex application to the simple instructions involves several layers of software that interpret or translate high level operations into simple computer, right? So uh, with applications being the outmost ring and a variety of system software sitting between the hardware and application software. So there are many types of system software, but two types of system softwares are central to every computer system today. One is an operating system and a compiler. An operating system interface between a user program and the hardware and provide a variety of services and supervised functions. So among the most important functions are handling basic input output operations, allocating storage and memory, providing for protected sharing of the computer among multiple applications using it simultaneously. Examples of operating systems in use today are Linux, iOS, and Windows. So, this system software, the software that provides service that are commonly useful, including operating systems, compilers, loaders, and assemblers. But whereas the operating system, that supervising program that manages the resources of a computer for the benefit of programs that run on the computer. So then comes to the compiler. So the compilers perform another the vital function, the translation of a program written in a high level language, such as such as uh, the you can see, you can implement any program, either the in C, C++, Python, or .NET. So any of the programs, if you take these programs, we used to call it as your the high level language programs. And these high level language programs are written in user understandable one, but that is not understandable by the the system. So these high-level languages such as the C, C++, Java, or Visual Basics into the instructions that the hardware can execute. So for that, these compilers are used. So given the sophistication of modern programming languages and the simplicity of the instruction executed by the hardware, the translation from high-level language program to hardware instruction is the complex part. Is the complex part. So for that, these high-level languages are going to be translated with the help of system software we call the compilation or interpretations. Okay, and these compilers will translate this high level language into the instructions, which is the machine understandable language. Okay, and from there it goes to whatever the converted code is there, that goes to the enter into the program, the operating system. So that is the program in computer instruction. So program instructor or program counter we used to say. So that goes to the program counter, and whatever the instructions are generated by the compilers, those instructions are executed by the operating system. So whatever the system softwares are generated, the system softwares, whatever the instructions are generated, those system software instructions will be executed by your operating system. So how? So from this program into your instructions, the operating system. So, but after they use the processors, or we call the CPU, central processing unit, or GPUs, etc. These processors are used to execute these programs or the computer instructions. So to execute that one, it requires the hardware part. So in the hardware, we will find the CPU, memory, as well as the peripherals. As we discussed, the main part of your computer are your CPU, memory, and peripherals. In previous lecture, we talked about the central processing unit, and the memory, that is the volatile memory and non-volatile memories, and peripheral devices, we talked about the input output devices. And from there, these hardwares are implemented with the what you call the another hardware part we call the transistors. So we talked about the generation of computers. In the generation of computers, we said the first generation they use the vacuum tubes, the vacuum tubes. Second generation they used the transistors. Then third generation used the ICs, integrated circuits. Fourth generation they use the VLSI, and fifth generation, and the present generation they are use the ultra VLSI technology transistors to implement this one. So in our course we are going to focus on this part. We are going to focus on the program in computer instruction and the operating system part. So here we are not going to talk about the system softwares, but we are going to talk about the operating system, the OS operating system. So this operating system plays an important role between the hardware and the software side. So that particular part we call it as your computer architecture. So in this computer architecture, the program in computer instruction is involved, operating system is involved for the performance and betterment of that one, and how those instructions are executed. This we are going to talk about this one. So in this case, if you see, uh, in this case, the high level languages to the language of your hardware, to actually speak to the electronic hardware, you need to send electrical signals. The transistors are, integrated circuits. So these are all electronic devices. So the easiest signal for computers to understand are the electric signals on and off. And so the computer alphabet is just two letters, just two letters. So just as 26 letters of English alphabet to, do not limit how much can be written, the two letters of computer alphabet do not limit what computers can do. So the two symbols of these two letters are the numbers zeros and ones. We used to call this as binary numbers. We'll talk about this, the binary number system, and that in the upcoming lecture series. But we call these are binary digit and also called bit. So one of two numbers in these, we write it as your base two by using zeros and ones, right? So the computers are, slaves to our, commands, so which are called instructions. So instructions, which are just a collection of bits that the computer understands and obeys, can be thought of as numbers, can be thought of as numbers. So these instructions are always in the form of zeros and ones. So these zeros and ones, how it comes. The first of, if you take any programs, those programs are in your high level language, as we are saying in C, C++, Python, then it requires a translator. We call that as interpreter or your assembler. So assembler is a program that translates a symbolic version of instructions into the binary version. Symbolic version of instruction into a binary version. That means if our program, high level language program is, suppose if I have addition of uh, A and B, suppose A and B. So this symbolic programs can be, these translators convert into, or assemblers convert into the zeros and one forms, zeros and one forms. Okay, so that we call the assembler part. So that assembler is known as your system software only, system software only, right? So the this name, the instructions tells the computer to add the two numbers A and B. The name combined for this symbolic language is still used as your assembly language, and in contrast, the binary language that the machine understand is machine language. So from this, you can see this we can call as your assembly language, and the zeros and ones which is written, we call it as your machine language. Machine language. Okay. So uh, once the machine language is there, then the recognition that a program could be written to translate a more powerful language into computer instruction was one of the great the breakthrough in the early days of computing. But programmers today owe their productivity and their sensitivity to creation of high level programming languages, right? So this is the high level programming language. We can say that a portable language such as we are saying here as C, C++, Java, Python, Visual Basics, that is composed of words and the algebraic notations that can be translated by a compiler into assembly language, right? So what is there under this one? Two key components of computers we call the input output devices, or input devices such as the microphone, and output devices such as the speakers, the name suggested. So what they do, They can take the input and the output as the result of your computation sent to the users. So some devices such as wireless networks provide both input and output to the computer. Input and output to the computer. So here, what is the case that we observe here is, just a second. Yeah. So you can see clearly here in this case. So whatever the application softwares, and your system softwares, they comes all the above part that comes as your software part. So there you can find the programming languages, and the compilers are used for their translation for applications, and the operating system when they are going to interact with the hardware part in computer architecture. We can say that it is completely divided into three parts: software and hardware part. In between that, your computer architecture plays a major role as an interface that consists of instruction set architecture, micro architecture, and the system architecture. So these computer architecture are able to interact with the hardware part, either with the transistors or the VLSI, very large scale integrator, in the fourth and fifth generation part. So what is the instruction set? So the first part in computer architecture, we always talk about the instruction set architecture, ISA. So ISA is set of computer instructions provided to programmers to implement the software. And this ISA is an abstract model of a computer, and ISA is implemented in microarchitecture by following the microprocessors language. So, what is microarchitecture? The microarchitecture, uh, the microarchitecture that actually implements the instruction sets in processors and the in processors. So for example, the address adders and the multipliers, these are means how you are going to performing the instruction of your adders and the multipliers. And this microarchitecture is about to ensuring instructions run correctly and quickly. And such microarchitectures we can see in the Intel and AMD. So these two microarchitectures have to implement the 8086 instruction set architectures. That's, these are two basics, 8086 architectures. So these are two basics of microarchitectures, and this are implemented with the help of the transistors. So transistors are made of your gates. So those gates follow some truth values, like AND gate, OR gate, NOT gate. So that we are going to discuss. So the first part of your computer architecture is instruction set architecture. One should understand, one programmer should understand what are the instruction set architecture is used by various the micro architectures or microprocessors. Then the next one is, the third very important part is system architecture. So in system architecture, any hardware implementation beyond processors, such as the memory allocation or memory organization or input output device functionality, that will be handled by your system architecture. So this system architecture is about to connecting processors and other devices, right? So this is the call of your what you call computer architecture. Computer architecture is an interface between the hardware and the software That computer architecture consists of three components. One is instruction set architecture, another one is microarchitecture, another one is system architecture. Right? So in this course, we are going to talk about, we are going to cover the few basic important concepts of your computer architecture. One is instruction set architecture. Then in the instruction set architecture, as just we spoke, every instruction is in the form of your zeros and ones. When zeros and ones are there, then how the arithmetic and logic operations like your addition of two numbers or multiplication of two numbers, or addition operation, multiplication operation, or division operation, or any logical operations like your and and operation, or operation, or NAND operation. So these how these operations are going to be performed. For that, the input is only zeros and ones. So we are going to talk about the computer arithmetic. That is, what is the binary form, what is the conversion from binary to decimal, binary, binary to decimal. So these topics we are going to cover in this computer arithmetic. Then we talk about the instruction level parallelism, that is pipelining. Then we talk about the speculative executions, that is branch prediction and the memory disambiguation. Then we talk about the memory hierarchy. In memory hierarchy, we talk about, mainly we focus about the cache organization. And then at the end of the course, we try to find or discuss about the modern parallel processors. Modern parallel processors. So the goal of computer architecture design is to provide easy to use instruction set and design the hardware to execute instructions correctly without any errors and the exceptions, and optimize the hardware management to execute instructions with the best possible performance. That means it gives the maximum instructions can be executed at a single time. So we focus on MIPS, millions of instructions per second, so that it can improve the performance of our computer. And mostly computer architectures is all about performance itself. How many instructions are executed per second, that is going to be discussed in this one. So the goal means provide easy to use instruction set, design hardware to execute instruction correctly, optimize the hardware management to execute instructions with best possible, and give the most better performance computer architecture design. So why we learn this computer architecture? That means it is all about the performance. So write efficient programs that requires understanding of computer architecture. Which architecture is following that computer? So one should understand to write the programs. So does the code has too much dependence between the instructions? That means, but that we are one should understand this one. Does the code has too much dependency between the instructions? So does the code using the cache efficiency or not to improve the performance of your computer? Why does this code run so slowly? So that difficulties needs to identify, and you need to understand how hardware components are utilized by your program to optimize your code so that the performance can be increased. So that means how many different functional units that you are using, whether in a single arithmetic and logic unit, single ALU is enough, or multiple ALUs are required. If multiple ALUs are required, then what will be the cost of your computer? So those things will be considered for the better performance and the low cost of your computers. And then this why we should learn about computer architecture means it is also about the correctness and the security. So the parallel programming means the same the single program can be divided into small programs, and those small programs can execute simultaneously. That we call the parallel programming is now an essential part of the modern software. So writing correct parallel program that requires understanding of parallel processor designs. How many processors are there? Okay, if the two processors are there, one processor may be used for integer performance, integer operation performance. Some are may use for your floating point, the performance, operation performance. So the micro architecture design have built-in security features. For example, the NX bit, that non-executable memory bit, is one example for providing the security. And some microarchitecture features are also causing security vulnerabilities. For example, the Spectre and the Meltdown are, these are two examples for saying that the security vulnerabilities in the architecture, computer architecture part. So, what are the concerns for your computer architecture design? The concern for this computer architecture design mainly the applications. So, what are the applications? The general purpose of these applications are like laptops and desktops. These, nowadays we are using, right? So, the productivity, interactive graphics, video, and audio. These are some of the applications. For that, one should understand the computer architecture design process, and at the same time it must optimize the price performance. That means by you must reduce the cost, not by compromising the number of transistors placing on a single chip in microprocessor. So examples, the Intel Core and AMD Ryzen are the examples of your general purpose, the laptop or desktop application area. Another one is the embedded computers. Embedded computers, that is the personal digital assistants or cell phones or the sensors. These are the embedded computers. These are another application of your computer architecture. These are also depends upon, these classes are also depends upon price and energy efficiency, as we discussed in previous session, that the classes of your computers, that is based on five, you know five categories. So there we talked about this PDM, your desktop servers, your cloud clusters, and your embedded computers part, right? And the commercial service and the scientific applications. In commercial service, what is the database size, how much database is used, then the transition processing and search engine and machine learning. So this is another application that is also depends upon the performance, availability, and scalability. So servers downtime could cost a broken company more than 6 million dollars per hour, right? Then scientific applications means protein folding, weather modeling, and the cambio defense. So in this scientific application, they basically follows the floating point arithmetic. The examples of these scientific applications are IBM Deep Blue and Cray, Tina, etc. So then comes to the great idea of what you call, yeah. Yeah, sorry. Uh, okay. So now we talk about the some of the great ideas in computer architecture. So we now introduce some, the great ideas that computer architects, have been invented in last the 60 years of computer design. These ideas are so powerful; they have lasted long after the first computer that use them. So with newer architect demonstrating their demonstration by limiting their predecessors. So these great ideas are themes that we will wave through this and the subsequent slides. So, to point out their influence in this section, we introduced the icon and highlighted terms that represent the great ideas, and we use them to identify the nearly 100 sections, the upcoming discussions. The first one comes that the design for more laws, or the great idea of your more laws. So what is this more law says basically? The one constant for computer designers is a rapid change, so which is driven largely by Moore's law. So it states that this Moore's law states that integrated circuit resources double every 18 to 24 months, every 18 to 24 months. So as we know that the current generation computers, they are following the ICs only, integrated circuits, correct? So in these integrated circuits, they were invented and in the year 1965. But what this Moore's law says that in every 18 to 20 months, these IC resources are doubling. These IC resources are doubling. So Moore's law resulted from 1965 prediction of such growth in IC capacity made by Gordon Moore, one of the founder of the Intel chip, or one of the founder of your Intel the processor. So in this graph, if you see in this the diagram, this is taken explains about the Intel itself by taking the history from 1962 2010. After 2010, the fifth generation started. So up to that, how he evaluated says that in every 18 to 24 months, the ICs are the number of transistors per die. They are increasingly, double. So here, what it says that this, Gordon Moore says that as computer designs can take years, the resources available per chip can easily double or quadruple between the start and finish of the project. Like a skeet shooter, the computer architects must anticipate where the technology will be and when the design finishes, rather than design for where it starts. So the Moore's law says that we use an up and to the right, the Moore's law graph here, to represent the designing rapid changes in his graph. If you see from here, the the first Intel microprocessor, given that Intel 4008, later it is doubled as 8080, then 8086, then 80286, then it reached in the year in between the 1985 to 1990, it is reached to by increasing the 1 million transistors. It is named as your I386 run, and the evaluation is going on up to 2010. So here every time it follows increasingly, okay, by double or quadruple. So the benefits of Moore's law says that from the previous graph you can identify, if there are more transistors, if transistors are increased, then opportunities for exploiting the parallelism in the instruction level parallelism, ILP, called instruction level parallelism. So instruction level parallelism is possible by increasing the more transistors on the microprocessor chip. So here, by increasing these more transistors, the pipeline or superscalar or very large scale, the very long instruction word or single instruction multiple data or vector, these are some of the instructions set architecture. These are some of the instructions which can be easily, the exploiting the parallelism by simply increasing the more transistors. Another benefit, says the Moore's law, is the general path of scaling. The general path of scaling. So, what is general path of scaling? By increasing more the transistors, the wide instruction issue, longer the pipeline. That means the number of instruction set can be increased from 1 to like n number of instructions and apply the pipeline with parallel. So some of the instruction from 1 to suppose 100 instructions are executed by one core, then from 101 to some 500 instructions will be executed by another core, and so and so. So that is the general path of scaling. The general path of scaling. And when this number of instructions are increased, then there should be a more speculation and more and large registers, and the cache is required to improve the performance of your computer. Another benefit is increasing circuit density. By increasing circuit density, increasing the frequency. When frequency is increasing, automatically increasing the performance. And another benefit is transparent to the user. So it is an easy job of getting better performance buying the faster processors. So faster processors means getting the more transistors. When more transistors are there, more path scaling will be possible. Where more path scaling possible, then increasing the frequency and the performance will be increased. When performance increase, it is very transparent to user, and user can prefer to use that. So this is the general observation and the benefits of your Moore's law. What are those? More transistors, general path of scaling, increasing circuit density, and transparent to the users. So then comes to the Dennard scaling. So we are going to talk about this Dennard scaling in the next lecture. Up to now, I'm going to stop this session here, and we are going to talk about the Dennard scaling in the next lecture.